Hey, what's up everybody? It's Rob with Sine Wave Specialists, and today we're going to go over the worst thing that you're going to run into in mechanical engineering or mechanical engineering technology, and that is thermodynamics. First video that we're going to do is this one. This is going to be based on interpolation. This is how to, get a value out of the table. We're not going to go into the book and do 60 versions of different things. We're just going to go over the basics. And from there, you can make the decision of how far you want to go. There will be one more video after this, hopefully posted same day. And what it will show is doing some of the examples like Brayton cycle or regen or how you're getting from one point to another in the system. But today, it's just the charts. You do not have to take this class and understand everything to pass it if you can do this. So go ahead, don't watch the video, and see what difference it makes for you. But I'm telling you, what I'm going to show you is how you get everybody from a fourth grader to do everything we've done so far in this class. There's only two methods. One, read the examples in the book. And two, know where to get the values. There's nothing else at all. Some of the common things that we're going to go over is we need to figure out these. These are what you're going to see in every one of the problems. You get pressure, temperature, specific volume, internal energy, enthalpy, and entropy. And then you're going to see a little TS diagram. This is a TS diagram. And what this is temperature versus in the domain of entropy. These are the tables at each one of these spaces here. So A, B, C, D, E. These are the tables. This is compressed liquid, saturated liquid, line, mixture. Everything in between these two lines is mixture, except the lines. D is a saturated vapor. E is a superheated table. And these are the tables where you get everything. Some of you are probably going to look in here and be like, why is A7 right here and A5? Because compressed liquid's only on A7. We will get to that. We will get to it. You've forgotten your chemistry stuff. I'm going to remind you. There's only 3 steps. Step 1 is identify the state of whatever's in here. Go to the table for that state, and then interpolate using known values. So you know something, or you wouldn't have been able to get to the table with it. So let's go over some of those examples. Alright, now what I've done is I've given you a problem. I wrote all this stuff down, kind of simplify the whole process instead of watching me write. So at 4 kPa, at 22 C, it's water. We need to find the enthalpy. So let's go through the steps. First step, identify the state. Where does it fall on this graph? Well, let's go and see. So at 4 kPa, which is right here, the saturation is 28.96. Okay, well the temperature is 28.96 there, but it's 22 here. So what does that mean? Well, at 22, it's lower than saturation, which means right here, this is where this number comes from. 28.96 degrees C at 4 kPa is B, because that is the line. That's the line it's on. But obviously our temperature is lower, this axis, so obviously we must be down here by A. Okay, so we're in compressed liquid. We figured out the state. It's compressed liquid. So what we do is we go over to the compressed liquid or compressed water table, and we look at the one for 4 kPa, which is blah 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 0.004 megapascals. Well, you'll notice it doesn't go below 5,000 kPa, and we're at 4. So do we interpolate? No, we do not interpolate. We will go back to the table for saturated water. Pressure table. Well, why? It's compressed liquid. Water is incompressible. It doesn't matter if it's a compressed liquid. So all those times you've been looking for a lower number than what was actually shown in the book, you didn't need it. The only reason the compressed liquid table exists is to add on to where this one stops at 22,000. It's not there because water is changing some chemical property. It's just there because you got really, really high numbers sometimes. And then there's like these normal numbers. So in our case, we're only going to use it to identify state. We know it's compressed liquid. We know that it's at 22 degrees C. So pressure is not a thing anymore. We're not worried about pressure anymore. So what we do is we know it's a compressed liquid, state A. So at 22C, what are we supposed to do? So we go over there, we look, and we can't find anything in one chapter. We can't find anything in A5. We can't find anything in A4. So how do we get the answer? Well, we need to interpolate. And we're going to go to table A5. Why? Because it's just easier. What you're going to do is identify everything, and then you're going to use the saturation temperature point. So now we're going to use the temperature. So it's 22 degrees C. So in that case, well, we can look at 4, and we know it's 28.96. But it doesn't matter if these match anymore because we already know what the state of the liquid is. So now that we know the state, what we can do is we can go in here and we can sum it up for 22 Celsius, which is these two. I know 2.5 and 3.0 is not the pressure. That doesn't matter anymore because the pressure doesn't change anything. We only care about the temperature and the enthalpy. And in order to get that, we need to interpolate between the two values. So we know that the enthalpy that we're looking for is right here. We know that the temperature we're looking for is over here. So now that we have a state, which is liquid, we go to the liquid table, water. And we interpolate. And this is how we do it. Right here. This is what we're looking to get to in the end state. Known high, known low, unknown high, unknown low, which turns into, we know the temperature, but we don't know the enthalpy. TH is whatever the number is above what we're looking for. So in this case, we have 22. So the next one up is 24.08. We can't go down because 2108 is not a high number compared to 22. So we know 22 is between these two, and the high number is 24, and the low number is 21.08. So we punch those in, and that's where these values come from. If you decide, for whatever reason, you want to use table A4, this is what it'll still look like. But these are the different values because 22 is between these two numbers on the chart. So let's look at it real quick. 22 is in between. It's in this big gap right here somewhere. So at 25, we'll come over here and we'll look at HF, which is 104.83, and then the low is 83.1 or 83.915. See? And that's what we put right here. And if you're stingy, you absolutely have to interpolate on a different table than what I'm using. I have done both right here to show you how that works. So what you're using is you're using your line equation, y equals mx plus b. You do your interpolation right here for this, for the slope. This is the A4, this is your pressure table, this is your temperature table. So as we go down through, or sorry, this is your temp table, this is your pressure table. As you go down through here, you can see how the numbers actually got punched in. Make sure when you punch them in to solve for B, you either pick both high numbers or you pick both low numbers. Remember, these are X and Y values, so the Y value needs to be temp, the X value needs to be H. So whatever's on the bottom is an X, whatever's on the top is a Y. If you use the H value, it's both H's. If you use the L value, it's both L's. And that goes for both sides. And then after you solve, you'll notice at the bottom that there's almost no difference in the enthalpy. And that is because of rounding. If I were to do this on a CAS system or a computer-aided system, this right here would have the same number because the chart is not different. It's just labeled differently. A4 and A5 are the same chart. They just use a different structure on the left side columns. They switch the temp pressures around. But it's the same values. Water is not changing because it's under a little bit of pressure. It's exactly the same thing as liquid water. So that is how you get your H values. Here I wrote just a little bit extra just for clarity. If you're going to use that temperature method, such as these, because you know that these temps stay the same all the time, it's always going to be 22C. Once you're on the right table and you have the option to search up all of these up here, your enthalpy, internal energy, entropy, all that, it's the same process. There's your entropy one, there's your enthalpy, there's your internal energy. You're able to search between all these values because you know one of them. So let's say you knew that your entropy at, I don't know, we'll say it's at 0.1 at 25C. Well, over here, 0.1 is a lot lower at 25C. 25C, 0.1 is a lot lower than this number. So we know that it's definitely a compressed liquid because it's this side of the line. It's not on the line, it's to the left of it. So it's compressed liquid. So we know we can still use this table. And we've used the 25C, and we can sit there and interpolate everything based on what we get for those numbers as well. So all you're doing is once you have a known value, you can interpolate everywhere from there. That's how you do it. Now when you get that value, that 0.1, we're going to do the same thing we did with the temperature. So we use that to know that we're in a saturated liquid, because at 25C, right here, I'll line that up for you. At 25C, we have lower than saturated liquid line. So we know we're in a compressed liquid, because right now it's at 0.3672. We're at a 0.1. We're at the right table. Now we don't care about what's over here. We only care about lining that entropy up with something. So what we do is we come over here and we look for somewhere where 0.1 is. 0.1 falls between 0.1511 and 0763 here. So when we do this, and let's say we have that entropy number for 25C, so we have 25C at S equals 0.1. From this value, we follow the steps again. Identify the state, go to the table, interpolate using known values. The state we just identified, it's 0.1 at 25C. There's 25C. Here's the entropy. Where does it fall? Does it fall in the mixture area in the middle between these two numbers? No. Does it fall above here and superheated? No. Does it fall below the 0.3672? Yes. So that means it's compressed. Because this value here is B value. We're over here though, because we're lower on the entropy. See, entropy is down here. So as we move toward the y-axis, entropy is getting smaller. So we're in compressed state, which, like we just said, is just water. So now that we know we're in just water, we can find out where that entropy sits, which is right here. 0.1511 and 0.0763. It falls somewhere in between here. So if they tell us we got to find, well, what's the enthalpy at this point, what I'll do is I'll come over here. And remember, known values go above unknown values. So I have SH minus SL because I know my entropy, but I don't know my enthalpy. So we got a high and low. So what we'll do is we'll look at our highs and lows as a liquid, the SF, between the values where 0.1 lies, which is 1511, 0.1511, minus the number below that, which is 763, 0.0763, and then our H value we don't know. So what we do is, at that same point, we look over at our H values, which in this case, HF, because it's a liquid, 42022 and 21020 line up with those two. So we know what's in between there. So we got 42.022, and then the one right below it is 21020. And that is the start of doing all of this. And you just follow it all the way down. You don't need anything else except this right here. And that's how it's done. Alright, now that we have learned how to get enthalpy, entropy, internal energy, pressure, temperature, and what am I missing? Yeah, all of those things in specific volume. Let's see if any of that actually matters. So if you look through here, you're going to notice that volume is given, all the temperatures, the pressures, all that kind of stuff is needed to be known. All you need to do is know the first part, which is already given to you. It already tells you what all this stuff is right up here to get this step. And then this step, and then this step. That's the first thing you solve. Then you go into pressure or process 1 to 2. And this one is on the ideal diesel cycle. If you look down through here, all of this stuff is stuff we just went over. The only thing you got to have is the volume, which is given in the step prior to that, and you can solve the whole thing. Let's go to something different. How about the ideal Brayton cycle? You know, turbines. If you look at what's given, and then you go over to what they're asking for, it's pressure, temperatures, and enthalpy. Well, funny thing is, we just went over how to find all of those. And then as you move through it, you just work from step to step. Let's do another one. This one is ideal reheat Rankine cycle. So twin turbine stuff. We go over here, temperature, enthalpy, pressure, enthalpies, entropies, pressures, temperatures, entropies, enthalpies. It's all stuff we already have. All you have to do is fill it in for the letter it tells you to fill in. Like, well, I don't know how to do the next step. Well, H2, H1, the pump, which is right there, it tells you how to get the pump from the specific volume and pressure, which is already something you figured out. It's all right there. You can solve the whole thing just by reading this example. One more just for fun. Look right here. All this difficulty. See that? See that right there? That is your cheat sheet right there. So when I come in here and I look at that TS diagram, here's how I picture it. I don't see this as being a bunch of values everywhere. I know that 1 and 2 are isentropic, 3 and 4, and then 6 and 7 are isentropic, 9 and 10, 11, 12, and 13. All of those that I just said equal each other are all the same S value. Everything this way has the same temperature value. Everything on the same horizontal line, even if it curves, like from 11 down to 6, that is equal pressure. So 11, 10, and 6 have the same pressure. 4, 5, 8, 7, and 9 all have the same pressure. 2 and 3, same pressure. 1 and 13, same pressure. 3 and 12, same pressure. So just from that, it should be pretty obvious on how to pick up almost 90% of your values just by looking at the example itself. Just the diagram alone pretty much gives you half the answers. And then you come over here, look at that. Everything we already knew. Enthalpy. That's all you need. The whole thing is pretty much just enthalpy. That's it. So when you get to the examples, just read the examples. Know how to use the chart. Know how to read the examples. If it says ideal Brayton cycle, go to the ideal Brayton cycle. Do the steps. This is how you pass the class. This is how you get 95 and higher on every test. Is you know how to read the material. If you understand the charts, you 90% of the time are going to understand the entire book. That's all I got for now. Pending any questions you may have, please leave them in the comments below. Leave a like. If you don't, oh well. It's not like I'm monetizing this channel anyway. But yeah, if you have any other questions regarding thermo, post them in the comments below and I will get to them. Have a good one.